On the 30th of November 2022, OpenAI released ChatGPT, which quickly became the fastest online product to reach 1 million users and also propelled large language models, LLMs, into the spotlight. More AI chat assistants have since sprung up like mushrooms, appearing in everyone's view. But do you really understand large language models? A large language model, or LLM, is a deep learning model designed for natural language-related tasks. Given some textual input, it can return corresponding output. Specific tasks it can accomplish include generation, classification, summarization, rewriting, and more. First, a large language model needs to undergo unsupervised learning on vast amounts of text. Taking GPT-3 as an example, its training data consists of multiple internet text corpora, covering online books, news articles, scientific papers, Wikipedia, social media posts, and so on. With the help of massive training text data, the model can better understand the relationships between words and their context, thereby improving its comprehension of text meaning and generating more accurate predictions. However, the large language models refers not only to the enormous training data, but also to the huge number of parameters. Parameters are internal variables of the model. Think of them as the knowledge the model acquires during training. They determine how the model responds to input data, and consequently, its behavior. Past research in language modeling has found that training models with more parameters, using more data and computing power, often leads to better performance. It is like teaching an AI to bake a cake. If you only allow the AI to adjust the amounts of flour, sugar, and eggs, versus allowing it to adjust flour, sugar, eggs, cream, milk, baking soda, cocoa powder, as well as oven time and temperature, the latter with more adjustable variables, enables the AI to better mimic and create a tastier cake. As the number of parameters increases, it might even gain the ability to create other things, inventing entirely new varieties. So today, the number of parameters in language models can be tens of thousands or even millions of times greater than before. Take OpenAI's first large model, GPT-1, as an example. It had 117 million parameters. GPT-2 had 1.5 billion parameters, and GPT-3 grew to 175 billion parameters. This allows large models, unlike smaller ones, to not be limited to single or a few specific tasks, but to possess much broader capabilities. For instance, previously we might have needed to train separate models for tasks like summarization, classification, extraction, etc. But now, one large model can handle all of these. AI chat assistants like ChatGPT, Claude, and others are all applications based on large language models. If the stunning debut of ChatGPT at the end of 2022 was a milestone that significantly raised public awareness of large language models, the technological development milestone actually dates back to 2017. In June 2017, the Google team published a paper, "Attention is All You Need," proposing the transformer architecture. Since then, the direction of natural language processing has been transformed, leading to a series of models based on the transformer architecture. In 2018, OpenAI released GPT 1.0 and Google released BERT. In 2019, OpenAI released GPT 2.0, Baidu released Ernie 1.0, and so on. So the development of large language models has long been in full swing. It is not that breakthroughs only happened in 2022, as many might think. But because ChatGPT was directly open to the public and allowed users to interact via conversation on a web page with a smooth and seamless experience, it captured the attention of the masses. The model behind ChatGPT, GPT, stands for Generative Pre-trained Transformer, indicating that transformer is key to its architecture. Therefore, to understand large language models, one cannot skip the transformer. Before the transformer architecture was proposed, the mainstream architecture for language models was mainly recurrent neural networks, RNNs. RNNs process text sequentially, word by word. The output at each step depends on the previous hidden state and the current input. Moreover, the current computation cannot proceed until the previous step is completed, making parallel computation impossible and training efficiency low. Additionally, RNNs are not good at handling long sequences, i.e., long texts. Due to the architectural characteristics of RNNs, the influence of earlier words on later ones weakens as the distance between them increases, making it difficult for RNNs to effectively capture long-range semantic dependencies. But in human natural language, it is very common for dependent information to be far apart. For example, in this sentence, the key to correctly predicting the next word is New York, which is quite far away. If an RNN were to generate the following content, by this point, it might have already forgotten the earlier information. To capture long-range dependencies, improved versions of RNNs later emerged, such as LSTM, Long Short-Term Memory Network. However, this still didn't solve the problem of traditional RNNs being unable to compute in parallel, and they still faced limitations when processing very long sequences. Then came the transformer, which has the ability to learn the relevance and context of all words in the input sequence, unaffected by short-term memory limitations. The key to achieving this lies in the transformer's self-attention mechanism. As the paper's title says, attention is all you need. Simply put, when the transformer processes each word, it not only pays attention to the word itself and its nearby words, but also to all other words in the input sequence, assigning different attention weights to each. These weights are gradually learned by the model during training through vast amounts of text. Thus, the transformer can understand how strongly the current word is related to other words and focus on the truly important parts of the import. Even if two words are far apart, the transformer can still capture the dependency between them. For example, in this case, grammatically speaking, it could refer to the closer street or the farther animal. Here, the self-attention mechanism captures a stronger relationship between it and animal, thus focusing more on animal. Besides the self-attention mechanism, another key innovation of the transformer is positional encoding. In language, order matters. Even if a sentence contains the same words, different orders can lead to vastly different meanings. That is why in the field of natural language processing, the term sequence is used. It denotes a series of elements arranged in a specific order. As mentioned earlier, RNNs, like humans reading text, process the input sequence sequentially, which creates a bottleneck in training speed because it can only be done serially, not in parallel, meaning it can't learn all information simultaneously. The transformer, before feeding words into the neural network, not only embeds the words converting them into vectors, i.e., representing each word as a series of numbers, but also represents each word's position in the sentence as a series of numbers, adding this to the input sequence's representation before giving it to the neural network. Thus, the model can understand both the meaning of each word and capture their positions in the sentence, thereby grasping the sequential relationships between different words. With positional encoding, words can be input to the transformer out of order. The model can process all positions in the input sequence simultaneously without needing to handle them one by one, like RNNs. During computation, each output can be calculated independently without waiting for results from other positions, greatly increasing training speed. With faster training, creating huge models isn't as difficult anymore, since the publication of attention is all you need. The transformer and its variants have been widely used to train large language models on massive datasets. Therefore, the transformer architecture is indispensable for the many powerful large language models we have today. If you are curious about how the transformer works in detail and how the GPT model behind ChatGPT generates text, the next section will provide a more detailed introduction. See you in the next video.